All right, as I said before, there is this new technology, somewhat recent, called the internet, and we're going to deal with that. So, no, 4chan is there. So, if we want to determine the percentage of people using email at 95% confidence level. So that was the goal. Now, that's not complete because now we inputting outside restrictions, and the outside restriction is what does the sample size need to be to ensure a margin of error of 4%. So that was the question we posed on Monday. We want to determine the percent of people using email at 95% confidence level. What does the sample size need to be to ensure a margin of error of 4%? Right, so there's two limitations. One is how sure you want to be that your answer is correct, and second one is how much wiggle room are you allowing yourself, your sample, to be away from what the population could be. All right, and there are two scenarios. Scenario number one is your assistant ran to the archives and pulled up an old study, and the old study said 16.9% of people used email in 1997, which we know is a very relevant year. Okay, nobody listens to jazz. 1997 is a very relevant year. All right, and so we try to solve this. If we assume that the study that has been done a couple years back, when we were all younger and prettier, when the study is relevant, we already have some value that we can bounce off. So when we look at margin of error, that was the formula, right? We knew what happens to the formula. We have an ability to plug in one of those values. Okay, so what we are trying to do is we're trying to create a confidence interval, right? And we need a margin of error, and this is the margin of error, and, well, 4%. So, in our deliberations on Monday, we created this formula. Yes? Yes. Everybody remember we went from there to here. Yes. Okay. So, let's plug it in. P hat and Q hat we know. We already have it here. So P hat right? Again, we assume success is using an email is success. So that's P hat. Well, what's Q hat? Well, Q hat is 1 minus P hat. So in our case, Q hat equals to 0.831. So we get Q hat. What else can we know? Well, we know what E is. E is 4%.
Do we convert that into 0.04?
Yes, 0.0, 0.04, yes. Because 4% we cannot really plug in, so we convert. What else do we need? We have p hat, q hat, we have e, we're missing z alpha over 2. So how do we get z alpha over 2? Well, either we remember what the critical value for 95 is, or alpha equals to 0.05, so alpha over 2 equals to 0.025. And we look up this number, and what do we get? Now, here's the question. How many of you are comfortable getting this number from the table? Everybody? If you're not comfortable, I would like to know now, because it's easier to fix it now than 5 days from now on Monday. Is everybody comfortable getting this number? No? Okay. So we look at the standard normal table. It's on the exact opposite on the other side of it. Okay. And what we're looking for is, we know that alpha over 2, it takes this little space. Right. So we're looking for, in that case, 0.025 here. If we look at for 0.250, we find it here. Okay? So the z-score is negative 196.
Okay.
That's it. That's how you do the quiz, that's how you do all this. Good? Good. Yes? I would do this one. And alpha over 2 is 0.0025, right? Which is 1.96. So we're looking, alpha over 2 is an area. So we're looking at it and it here. So we're looking for 0.025. We find it here. Which means that the z-score attached to it, or critical value, is negative 1.96. Good?
Oh, that's it?
That's it.
Okay.
That's how you do the quiz, that's how you do all those. Everybody else peachy? Yes?
Yes,
You guess, you know.
yeah.
You're good. Okay. If you change your mind, let me know. All right. So we find the critical value. So now we have everything. So let's plug it in. N equals to z alpha over 2 squared, p hat, q hat divided by e squared. So n equals to 1.96 times 0.169 times 0.831. Critical value p hat q hat divided by e squared, which is 0.04 squared. And after multiplying it out, I got this. You should get something very similar depending on how much you round it.
I didn't square the 4, I just went by 16. So you gotta double that number, I think.
Like 16 flat or 0.16?
No, I think it was 16.
If it's 16 flat, you're off by a factor of
I did-
100.
It's like 671. I think that was our sample size. I did something wrong at the bottom.
Oh. That's okay. I'm going to find it. And I'm going to point it out. All right. This is what we get. And here comes the question which... So aside of making little mistakes like forgetting squares or putting 4 instead of 0.04 here, aside of those little mistakes, here's the most common mistake. Is this the answer to our question? Is this a correct answer?
You want a sentence?
Sorry?
Oh, wait.
Round it.
Why?
If you need
Oh, for people.
'cause it can help.
19.4% of a person?
Yeah.
You haven't seen my freezer. Angelica has been divvied up.
Yeah, it's not that.
Sorry?
That's
You just
on camera.
incriminated yourself.
Yeah, it's...
And you're recording.
Well, yeah, I'm not worried. The idea is people will get caught up with numbers. Everybody does, eventually. And eventually you get to here and you're going to put this on an exam or a homework. And I'm going to look at it and I'm like, okay, well, great. Don't invite me to dinner. Don't serve me Chianti, right? This is problematic. Again, because we are doing... Now, are we rounding it down or up?
Down.
Why? Why each one? I hear down and up.
Oh, we want to make sure we have, have
If you round it down, and we ask less people, then our margin of error will be
Greater.
close to 4 but slightly bigger, right? And this is the cutoff that we are given. If you round it up, yes, we have to give out one more survey, we have to ask one more person, but on the other hand, our margin of error will be just shy of 4. Okay? So the answer to that is okay. But again, we know how relevant data from 1997 when it comes to the internets is, right? Things weren't happening back then. So what happens if we don't know anything? You know, your assistant brings out the paper from the survey from 1997 and you have an accident, you know, kind of a oops moment, spill coffee, put it in a shredder, you know, put it in a burn bag. It's kind of like, oh well. So part 2 of the question was, what if we have no baseline or basic? Well, no, we have.
No, nothing about the email usage.
Yeah, we have no basic idea. I'm going to put basic in quotation marks. Yeah. We have nothing to base it on, right? Here we had something, so we were hoping that those numbers would be relevant. Maybe different, but relevant. Right? Here we say, hey, this is 20 years ago. The number's obviously different. Let's assume we don't know. If we assume that we don't know, we're going to assume the worst case scenario. So assume worst case scenario. Assume the worst case scenario. Well, what's the worst case scenario? 0.5, 0.5, exactly. Well, as we talked on Monday, if you have 90% success rate of doing something, you're probably going to do it. If you have 10% success rate, you probably won't do it. The most difficult decisions are 50-50. Right? So 0.5, 0.5, which means that our calculation now turns into z alpha over 2 squared, 0. Divided by 0.5. Turns into that. All right, we plug in the numbers. I'll get 600 and a quarter. $600 and a quarter, right? So 600 people and a leg and an arm. It's almost a person, right? And so the answer again turns out to be rounded up because we're talking about human beings, and it's 601. This example illustrates something very, very special. And what it illustrates is that if we have some idea of what the sample is going to show us, we can cut down on the number of surveys we have to do very dramatically. You had a question?
I was wondering if I can use this formula and verb that I have to get this number.
Isn't that the same one?
Because yours has the square root and this one doesn't.
No, the square root is for e. I'm using n. You see this one and the board here? Your book just puts those together and squares the whole thing, which is the same thing. Right? So if we have any idea of how the sample is going to respond, how the population is going to behave, we have some inkling, right? Or we do a quick study beforehand, run a small sample just to figure out what people trend to be like before we run the big study, we can cut down on the number of surveys. Best case scenario, surveys are about 5 to 15 cents a survey. Worst case scenario, the surveys are about $10 to $15 per survey.
Wait, how did you get 1.96 on the chart?
This, here,
Oh, wait.
that's the same one.
Oh, wait, yeah, never mind.
That's okay. No, that's okay. It's Wednesday, apparently. Apparently, that's a new excuse. I'm going to go home. My girlfriend's going to tell me the dishes. I'm like, no dishes! No dishes! It's Wednesday. Flip the table. That's going to be difficult, though. Yeah, that I didn't think that completely through. That's a good point. That's a good point.
Implying we're not cleaning tonight.
Wow. God damn it. Yes.
You got 1.96 times 0.25 divided by 0.04 squared, and you get.
Oh, I need a square. Yes.
Oh, there you go.
Thank you. Okay, one person paying attention. All right, any other questions? Sorry? Makes a difference?
Yes.
Okay, let's move on.
I had a question. So what if n comes out to like 600?
Perfectly 600?
Will it come out perfectly? Number?
There is
You
a
always have to round up. So
no,
just say
no. So you could get 600.
Yeah.
If you get 600.00, then 600 is the answer. But the chances of getting 600 exactly,
Slim.
I haven't had a problem yet
Like that.
that would get exactly 600. Some cases you get very close.
So no matter what point you get,
I would definitely round up. Now again, depending of where you round in the middle of the problem, you could probably, but that's a conversation about specific numbers. Okay. Sometimes you want to check somebody else's work. No, we don't check. You don't audit things. You just submit numbers and nobody cares. We're not talking about Pentagon spending. We're talking about public administration. You check. So, given a confidence interval, find p hat and e. Right? If you get a confidence interval, you get two numbers, and you say, hey, the population proportion is somewhere between those two numbers. That's not always a great thing. Sometimes you want to know what the margin of error was implied. And so what is a confidence interval? Well, it's p hat minus e less than p hat plus e. That was the confidence. It's two numbers. So how do we find it? I understand that some of you might be visual learners, so I'm going to draw pictures. If we have p minus e, so we have p hat minus e, and we have p hat plus e.
What does the line represent?
This is p hat minus e, p hat plus e. Those are two numbers. I found it that most people respond better to visual than a formula. I'm going to put the formula now. If I'm trying to find p, right? If I add those two things together, so I go p hat plus e plus p hat minus e, what do I get out of this? E minus e will cancel out, and I'll get 2 p hat. If I divide by 2, I can get p hat. So if I add those two pieces together, one is missing a piece called e, and one has an extra piece e. If I add them together and divide by 2, I'm going to get. So p hat is the upper plus the lower divided by 2. That's the formula, right? On the other hand, when we are talking about E, the difference between this and this is what? Is two E's, right? That's an E. That's an E. So how do we get that? We take the upper minus the lower. This will give us this little section, and divide by 2. So E is upper minus lower divided by 2, which is p hat minus p hat 0, e minus minus e, that's 2 e's, right? That comes out to be 2e over 2. So upper minus lower divided by 2. Okay, let's do an example, quick example. So a good example is on the news. You get to see. So example, we have some news, and the news say at 95% confidence level, we have a confidence interval that is
I have a question
yeah.
on the second formula. It looks like I don't understand how you get 2 e's instead of 2 p's.
P, you open the parentheses, that's a minus p plus e, right?
Okay. Yeah.
P minus p 0, e plus e
Okay.
2 e's.
Because the minus
Yeah.
times the minus.
Yeah.
So negative times the negative is nothing.
All right, so let's say this. We have some news, and the news are saying at confidence level of 95, the confidence interval is this. What was our sample proportion? What was our margin of error? Sorry?
Are you talking about the other question?
This is an example we're going to do for this, right? So question is what p hat. Well, p hat is upper, so 0.81 plus lower, 58 divided by 2. And that comes out to be 0.695. And what's E? Well, E is upper minus lower. Divided by 2. And that comes out to be okay. So if you want to check somebody's work and you don't know what margins of error they used, but they give you the confidence interval, you can get the margins of error out of it. It's also pretty good to check somebody else's work if you're helping other people. Okay. Let's try another example. One example is in a study of 1,300 randomly selected stat students, 900 of them passed stats. And here's part A. Part A says find the best point estimate for population proportion. Part B. Construct a 99% confidence interval. And part C are most students passing. And when it comes to this little section, this is the type of question that is checking all of your little tricks. So how do we do it? Oh, first we're going to start with part A. So what's a point estimate? Sorry. Says mean.
Single value used to approximate population parameter.
Yes, single value. So what's our single value?
No,
900, 1300.
Mm-hmm.
42, right? Answer to the universe, 42. It's not, it's 17 pi over 22. But, you know, aside the point.
Oh, it's 900 divided by 1300?
It's the sample proportion, which we defined as x divided by n. So in our case, we defined it as 900 over 1300, which comes out to be like 69 something, 69.3. Is this the best? It's the only one we have. When you have only one option, you don't have options. So question of the best is a tricky part. This is the point estimate from this example with no other data available. This is the only thing we can have. Right? We are guessing the population who is going to behave like our sample that we took randomly from the population. How precise is it? We don't know. But if you had to guess where it's going to be at, it's going to be at 69%. All right, part 2, or part B. Construct a 99% confidence interval. Well, what's a confidence interval? We covered that. That's p hat minus e less than p hat plus e. Right, that's a confidence interval. Well, what do we need for it? P hat we already have. We need e for that, right? And how did we find e? We defined e as z alpha over 2 p hat q hat divided by n under a square root. Okay, let's go. P hat, we have q hat. Well, we know what q hat is because q hat equals to 1 minus p hat. So in our case, q hat equals to 0.3077. So we have q hat. So we have p hat, we have q hat. What's n?
1300.
Right? N is the size of the sample. And our sample is 1300. So we have n equal to 1300. And then comes the question of what's z alpha over 2.
Draw the picture.
Yes, z alpha over 2 is a critical value. So what are we putting in the middle? We wanted 99%, so 0.99. So alpha is 0.01. So alpha over 2 equals to 0.005. Alpha over 2 equals to 0.005. So now we look up. Again, every number that is concerned in this space under the curve is either area or probability, which means that when we look at our table, this number can be found here somewhere, right? When we're talking about things on the axis and on the axis alone, we're talking about the z-scores which are on the outside.
Maybe 24575. Do you want to go that far? No.
Yes, that's one of those three numbers that I would like an extra one. That's a minus. And this is okay, so we have z alpha over 2. We have p hat, we have q hat, we have n, we have z alpha over 2. So let's find e. So e equals to 2.575 times square root of 0.6923 times 0.3077 divided by 1300. Is everybody comfortable with finding q hat, finding n, finding z alpha over 2? Yes, no, maybe.
I just have a question
Yeah.
about the chart. It's a little bit confusing.
Okay.
Find the z off over 2.
Yeah. What I would do is I would do alpha over 2 on the left side.
Okay.
And now we're looking for alpha over 2 and
1.9. But we don't look at the...
1.9. We're going further, further, further. So that was 1, right? This is almost right. We need one extra 0. So we're going up and we find it.
Right there.
Yeah,
Okay.
that's this number right here between those two.
Okay.
Okay, and then we get e to b 0.033. Now, if you plug it in a calculator, I recommend this times this, then divided by this, then square root the answer, then multiply it times this. Go from inside out versus from the outside in. Okay. And the last question, oh no, we have to finish it. All right, so the confidence interval is p hat minus e. P hat is here, e is there, so we get 0.6593 less than p less than 0.7253. And then here's the confidence interval. Questions? Guys, there's no shame in getting lost somewhere. If you don't know what to ask, just tell me where you lost me or when I lost you.
Where did 6593 come from?
This?
Yeah.
This is this. This is the confidence interval. So I took this minus this gives me this number, and this plus this gives me this number. Good question. Anything else? All right. So, part 3, are most students passing?
Yes.
Yes. Why?
Better than 60. 60 is passing, right?
Passing is sure, but we can say 50 is passing, whatever, right? Whatever the number here is passing, 60 is passing, fine. This is saying, hey, the population proportion is somewhere between 66 and 73%. Yes? Are most people passing? Well, most, depending on how you define it. I define it as bigger than 50. 50.1 is more than the other side, so it's most, right? So as long as both numbers are bigger than 50%, it's passing. Because I'm saying, hey, I'm 99% sure that my population proportion will end up being between 66 and 73%. Okay. Now, a trick case looks the following. That's a tricky question. Are most people passing in this example? I'm going to roll it over. but there's not a middle.
So it's just a rate.
This is, I'm saying, I'm 99% sure the population proportion will end up between those two numbers. It can end up anywhere between those two numbers.
We don't know.
Right? Most politicians and most people that don't do statistics and most PR people and marketing and couple CEOs will look at this and be like, of course most people are passing. The average is right close to 60. But it's not the average. This is where it can get hit, right? This isn't just a random two numbers you can average. This is an actual, hey, is this going to work? Now, the question that follows, this type of question is, how can we get an interval where most people are passing? How do we produce an interval where most people are passing? There are two ways to do it, right? We know that p hat is where? What's p hat for this? It's this plus this divided by 2, right? Which came out to be 0.59, right? P hat is there. So what we cannot change p hat, really, because that's the sample we get. What we have is we have an e. If we can get the e to be smaller, we're going to tighten the interval. And there are two ways to make the margin of error smaller. There are two ways that you can control. One is if you increase the sample size, your margin of error will be smaller. Right? If you ask 5 people about an opinion, you will have a guess of what everybody else does. You ask 5 million, you're going to have a really, really good idea of what people are doing. So increase the sample size. Second thing is if you take your confidence level and you drop it, you go from 99% sure to 90% sure or 95% sure, your E is going to drop as well. If we drop the confidence level, we are lowering the critical value. If we are lowering the critical value, we are lowering E. So if you ever get into the point where this is what you got from your calculations, but you really, really want to show that most things are happening, there are two ways to do it. Take a bigger sample or be less confident about it. Right? I mean, remember, the moment we're starting to talk about confidence, we are toying with faith. And I'm going to use faith here. Right? Why we are toying with faith? Because in this case, and in this case, there's always 1% chance you got it wrong.
So is that how you can manipulate statistics?
Yeah, a little bit.
So if you don't want like that answer, you change something else.
Well, I just take a bigger sample. If I take a bigger sample, the margin of error is going to tighten, which means that I'm going to have both numbers above 50. Or I get my confidence level. If I drop my confidence level to 95, that's usually probably enough to tighten the whole thing down. It's a very nice way to do it, right? Yes.
This is what they do for elections, right? When they put up like polls for elections, they put this like at the bottom.
No, for most elections, for most of the stats that they put in most of the stats that you see on the news, they will put two things on the bottom. They will say that the margin of error is about 1%. They will say that on the bottom. Then they will tell you some n. Usually, and I'm going to huge air quotes here, usually that number should be around 300 to 1,000 people. That's usually what they put, but not necessarily. They need to put this, they need to put this. And then they can tell you, hey, well, 40% of people do something. If they tell you 40% people do something and they don't tell you anything else, that's a made-up statistic. Somewhere they need to show an E and somewhere they need to tell you how big your sample were. And now, the assumption is going to be that it's 90, 95, or 99%. Which also should be somewhere done. So when you're looking at headlines, usually somewhere in the bottom or on the back page or on the website, they have this, this, and this. Because this by itself is meaningless.
What if they have a huge margin of error, like 12%?
Then they have 12%. They had a huge margin of error, probably because they were trying to be very confident, or their sample was very, very small. If you have 12% margin of error,
That's what happens with like a lot of the polls.
no. With the polls, there's difference. So when they have polls and they have exit polls. Polls are what people actually put in. Exit polls is we're going to catch people that are coming out and we're going to ask them. And the most popular one that I like to bring up is in New York, the race between Hillary Clinton and Bernie Sanders. The poll and the exit poll difference was 12%. Okay. UN intervenes if the difference is bigger than 1%. So in Serbia, when there were elections and the difference between exit polls and actual polls were 1.5%, UN started looking into election fraud. So if that difference starts reaching 2%, people get really, really worried everywhere. Except in New York, because 12% is just normal. I don't know if it's a lie. I don't know if people who lied about who they voted for, right? Because that's a common case. But exit polls are usually spot on. If you ask enough people, exit polls are usually spot on to what the actual results should be. How accurate? Most people claim within 1% difference. 12 gets me worried. I don't know what happened. 12 gets me worried.
But sometimes on TV you see like 3 out of 4 dentists, but the 5 points are so small you can't even tell.
Well, 3 out of 4 dentists that we hire to tell us their opinion, right? It's a question how you take your samples. Is it a convenient sample or is it a random sample?
It's just a statistical manipulation.
No. We gave you all the data just because you cannot read
But
it.
in fine prints where
Yeah, but if you cannot read it, it's not my fault. Well, I'm not worried about dentists, really. Let's be honest. I'm worried about companies that produce fentanyl. Fentanyl is a really, really awesome opiate that is designed to kill pain. And it's way stronger than morphine and is designed for people that cannot handle morphine because of it. And was designed, from my understanding, limited understanding, it was designed to help people that are dying out of cancer, to help them go through the whole dying process easier, because morphine is no longer working. And that was the design for it. Companies that produce fentanyl are giving kickbacks to doctors, paid speeches, cruises. So people that get their tonsils removed, rather than getting an ibuprofen, get fentanyl. Sorry?
That looks great on the battlefield too.
Yeah, well, let's make a difference between getting shot by shrapnel and tonsils. There's a huge difference, and I seen the scars from removal of tonsils, and I seen an R4 grenade shrapnel. There is a mild difference. I mean, I don't want to pick teeth, but when you have 4 ribs missing because a piece of metal about E big tore through your body and your bulletproof vest, there's a difference. I mean,
it's post-surgical use, but it's the mechanism of release. They tell you can't use it with heat because it releases faster.
yeah, well, there's a lot of those things. Oh, by the way, Oxy is legal to prescribe to 11-year-olds.
Oh, what?
Oxycontin. Oh, by the way, Oxycontin accounts for 60% of the deaths from opiate abuse. It beats heroin. Black tar heroin is less toxic and kills less people than oxy. Fun statistics.
I think there's a trillion oxycontin pills out there.
All right. Shall we do more? Yeah. Yeah. Okay. We talked about what? Help. Mondays you guys are very work. Wednesday is not. Seriously, do I need to bring my stash of crystal meth and we can just, pop a pill and do stuff?
You could just bring food. You could just bring, I don't think it does.
Pizza Wednesday.
It's Wednesday.
I has mints. Mints. So we talk about proportions, but proportions aren't all of it. Let's talk about means. Yay, means. All right, so first couple of things we should talk about. One is just so we don't get the 3 out of 4 dentists. I asked 4 dentists, 3 of them are my friends, 3 out of 4 dentists. Right? We need a random sample. And I cannot stress enough how important is it to have a random sample. So that's one. Two is population standard deviation, sigma, is assumed to be known. Now, one can ask, why are we trying to find out population mean if we already have population standard deviation? The reason why we are assuming we know the standard deviation is because we need to go through the process of learning how to do this before I throw you on the deep end of the pool without the knowledge. So, 3, n needs to be bigger than 30. Or population is normally distributed. Now again, why do I say that? And bigger than 30 population normally distributed? Because those are conditions 1 and 2 for what? N bigger than 30, sample bigger than 30, or population is normally distributed, are 2 rules for what? What was that thing called? Well, come on. Yeah.
Central limit theory?
Yeah. Central limit theorem, right? If you don't have that, right, we're running into the third section. So if it's bigger than 30, we don't care what the population is like distributed. If it's less than 30, we would like it to be normally distributed. That's why we can use the formulas. All right, let's go further. The point estimate. Anybody want to take a wild guess what's the point estimate for population mean? No? How about sample mean? Right? We had sample proportion for population proportion. We have sample mean for population mean. All right. Margin of error. What's margin of error? Well, margin of error is 2e. It's still z alpha over 2. But in here we have Yes. So sigma divided by square root of n. So far nothing changed, right? The formula is slightly different, but we get the same thing the same way. So confidence interval, what would confidence interval look like? Will look like x bar minus e less than mu less than x bar plus e. So confidence interval would be that. Now why I'm plowing through this so quickly? Because we did this. The e changed a little bit. Instead of p hat we have x bar. Instead of p we have mu. So there's little changes, but overall the procedure and how to get there is exactly the same. So how do we get this whole thing? Well, the steps are very similar. One, check requirements. Two, critical value. Three, again, the procedure is very, very similar to what we already been doing. Check requirements, yes. Before we had requirements, p hat times n needs to be bigger or equal to 5, n times q hat needs to be bigger than or equal to 5. This time around, is population normal or is our sample big enough? One or the other, or both. Finding critical value. Again, we have a confidence level finding critical value. We did this. We know how to do this. E, yes, we plugging in slightly different numbers, but we can do that. And then confidence interval, we build it the same way. We started with proportion because proportions are easier to deal with. So we have 5.5 minutes left. How about I put a problem up for you to do by Monday? Let's call it extra credit. If you don't do it Monday, I will go over it again. I think that's a nice way to, get you excited about homework. I call it extra credit, right? Even though I'm gonna curve the class afterwards for all the extra credits. It's like in the military. You don't want to do more than 5% over what's required because they will start expecting the 5%, and then 5 years from now you're gonna be like, I'm doing 5 times this work. I'm like, yep, you shouldn't have been advancing so fast. All right, so the problem is the following. Random sample of 40 students. You take a random sample of 40 students. The average resting heart rate for the sample was 76.3 beats per minute. Assuming the population standard deviation is 12.5 beats per minute. 12.5 beats per minute. Construct a 99% confidence interval for the average resting heart random sample of 40 students. The average resting heart rate for the sample was 76.3 beats per minute. Assuming the population standard deviation is 12.5 beats per minute, construct a 99% confidence interval for the average resting heart rate of the population.